Hi everyone, and welcome back to our YouTube channel. In this lecture, I will show you what a consistent system is and what an inconsistent system is. And in addition to giving the definition of an inconsistent system, we will also examine how we can determine whether or not a given system is consistent or not. Alright then, having said that, let's start with the definition of a consistent system. And here's the definition. Alright, if a system has at least one solution, it is called consistent. Otherwise, so what I mean by saying otherwise, it means that if it doesn't have a solution, then it is said to be inconsistent. Alright, okay, let's look into that. Well, first of all, so far we have both homogeneous systems and non-homogeneous systems at hand. This is what we have learned, and we also learned how to solve such systems. And let's think about this definition before starting to show how we can determine whether or not a given system is consistent. Okay, here's the thing. If the system is consistent, then it must have at least one solution, which means it can either have one solution that is the unique solution case. We already know, right? We have only one solution that satisfies both equations at the same time. That's why it's called a unique solution, right? So this is one of the cases we can run into while solving the systems. And we all know that we have three different possibilities when we are trying to solve a system. And the first possibility is having a unique solution, where we have only one solution, okay? And how about the other two possibilities? Well, another one is that we can also have an infinite number of solutions, right? This is another possibility. So we can also have infinite number of solutions. Many infinitely points can satisfy both equations at the same time. So if these two cases occur, then we have that our system is consistent. This is the logical expansion of the definition, right? If a system is consistent, it must have at least one solution. That means we can have one solution or we can have more solutions, right? And in our case, it is corresponding to having infinite number of solutions. And these two cases refer to consistent systems. How about inconsistent ones? Okay, we said otherwise, so which means if we have no solution. And actually this is our third case, right? We know we have three different possibilities. We can have unique solution, we can have infinite number of solutions, and we can have no solution at all, right? This is another possibility. No solution. And if we don't have a solution to the given system, then this system is called inconsistent. Inconsistent. So let's recap so far. If you want to show that a system is consistent, then we need to show or prove that the system should have either a unique solution or an infinite number of solutions. Whereas if you want to show that a system is inconsistent, then we should show that this system has no solution. In other words, the solution set is the empty set, right? And other way around it, to say it, right, there is no tuple that satisfies both equations at the same time when we have an empty set corresponding to the solution set. Okay. All right. Now, before diving into how we can show that, let's continue to think about this definition a little more. As I said earlier, we have two kinds of systems, right? Homogeneous systems and non-homogeneous systems. And in the case of having a homogeneous system, we know that all the right-hand side values are equal to 0, as we learned in our previous lectures. And in that case, we know that a homogeneous system has either a trivial solution or a non-trivial solution. So if we have an homogeneous system, do we actually need to check to see whether or not our system is consistent? No, we don't need to do that. Why? Well, because we are ensured that we have two possibilities. One is the trivial solution case, right? The trivial solution case, and while the other one is the non-trivial solution case. Non-trivial. And in the trivial solution case, we know that we have at least one solution that satisfies both equations at the same times. And what is that? That is the point. Suppose we have n unknowns, right? And the n tuple that includes only zeros is called the trivial solutions, because when we put these values in our equation, all the left hand side values are equal to 0 and all the right hand side are equal to 0, and 0 is equal to 0 is satisfied at any time for any unknown variables, right? So for any coefficient actually. So we have at least one solution. And in the non-trivial case, what we have the infinite number of solutions, right? As you remember, we formed the general solution in terms of free variables in that case, so we can have also an infinite number of solutions. But in either case, when we are given a homogeneous system, we are ensured that we have one of these two possibilities, so we don't need to check to see if a homogeneous system is consistent or not, because it's already consistent, because we already have known that we have at least a trivial solution. Alright then, so what we need to do is we need to check to see whether or not a non-homogeneous system is consistent. Alright, and now here's the question, how can we determine actually whether or not a given non-homogeneous system is consistent? Okay, let's give an example for that situation. Here's the example. Let's say here's the first equation, x1 minus 2x2, sorry, x1 plus 2x2 minus 3x3, say equal to 5. Okay, suppose this is the first equation given, and say this another equation, let's say 3x1 plus 6x2 minus 9x3 is equal to, say what? Say 20. Okay. Now suppose we are given this system where we have two equations and three unknown variables, and the question is that, is this system consistent? Okay, here's the question asked, and we need to show that it is consistent or not. Okay, here's the question, and let's solve it. So what we should do, doesn't matter which technique we use, the thing that we need to show is clear, right? So we need to somehow find a manner to understand whether or not the system is consistent. In other words, to be consistent, this system must have at least one solution. So it could be the unique solution case or it could be the infinite solution case, but it must have at least one solution. Then we can say that yes, this system is consistent. Alright then, let's use Gaussian elimination method, and here let's represent the system in the augmented matrix form and write down the first coefficients, right, and then the right hand side values, don't forget to put them, right, and then we have 3, 6, minus 9 and 20, right? So okay, and let's check the first pivot element, right? The first row is a non-zero row and the leading entry, which is 1, is the pivot element. So I should eliminate the values below the pivot element, which is 3 actually here. So this 3 should turn into 0. And how can I do that? I need to replace row 2 by performing an elementary row operation. Alright, row 2 plus plus what? Minus 3 times row 1 would work out, right? So just this would take us to where we want to go. All right, now the first row is the same, no change. I just put its values here. Oops, sorry, and this value, right? There is no minus sign here. Okay, this is 5. Oops, sorry. Yep, this is 5. And what has changed is the second row, right? The values in the second row have been changed in the meanwhile after applying this modification. Okay, so R2 plus minus 3R1, this is 0. And if you notice, this is also 0, this is also 0, and this is 5. Okay, so now I check to see whether or not this is in row echelon form, and yeah, we have the first pivot element, we have this value is equal to 0, and we're done, right? We have strictly increasing number of zeros starting from the top row to the bottom row, so this matrix we find is in row echelon form, and we're done with Gaussian elimination method. So what we have found? Let's examine the last row, guys. So, and again, remember what we are looking for. So we are trying to see whether or not this system is consistent, and we somehow find a way to determine to this question, to the answer of this question actually, right? So look at the last row. So what we have here. So if I write it down here, by applying back substitution method, we have 0x1 plus 0 times x2, right? These are the coefficients of the unknown variables, and 0x3 is equal to 5. So what? So what we have found? You see, the left-hand side, regardless of the values of the unknown variables, is equal to 0. In either case, doesn't matter what the values of the unknown variables are, right? So the left-hand side would always be 0. But on the right-hand side, we have 5. So we obtained a result something like 0 is equal to 5, but this is not possible, right? Numerically, this is not true. This is false, right? So how can we conclude this section? So this means that actually we have no solution case. Why? Because regardless of the selection of the values of unknown variables, we come to a point saying that 0 is equal to 5, which is always false. Which means that we have no 3 tuple that satisfy both equations at the same time. So this is how we can decide whether or not we have at least a solution. So you see that we have the empty solution set in this problem, what we found. So no solution, right? No solution, because we reached to a very ridiculous result saying that 0 is equal to 5. So algebraically, this is always false. And this is how I decide the system has no solution. After we are done with the elimination process, doesn't matter which technique we use, Gaussian elimination or Gauss-Jordan. So if you run into a row, like the second row here, saying that some values equal to another, some real values which are different than each other, then this is always false. That means no tuple satisfies this equation. And in this case, we have no solution to our given system. And this is the empty solution case. And therefore, our result is, our conclusion is, right, this is an inconsistent system, right? So the system I tried to solve here is inconsistent, which means that there is no solution. So the solution set is empty set. Okay, can we generalize this conclusion? Yes, we can. So here's the thing. No matter what kind of system we are given, the number of equations, the number of unknown variables, or the values of right hand side values can change. That doesn't matter. What we are looking for is, we are looking at the row echelon form that we obtained in the end, or the reduced row echelon form, doesn't matter what it is. So if we have a row like this, let's generalize this idea. So on the left hand side, a finite sequence of zeros up to the point of our vertical line where we store the right hand side values, right? And then here we have a value b, and here b is different from 0. And in this case, we have no solution, guys. So our formula, or the way we check, is we look at all the rows that we obtained in the end of the elimination process, and if we have any row in this form, any row, doesn't matter where it is, but in the echelon form, if we have a row of something like this, in other words, a bunch of zeros up to the right hand side value, and then a right hand side value which is different than 0. So in this case, no matter what the value is b is, we have something like 0 plus 0 plus 0 blah blah. 0 is equal to something that is not equal to 0, a b value which is not 0. So this will never satisfy, right? So we have the no solution case, and therefore we can conclude that our system is inconsistent. All right, so let's give another example. Let's say another example. Now we know how we can determine whether a system is inconsistent or not. So we check a row, right? We check all the rows, and we want to see if we have a row in this form, right? A bunch of zeros up to the right hand side value which is not equal to 0, and then we have a false result. Then we say that the system is inconsistent. Okay, let's look at another example. So say x1 minus x2 is equal to, say 1 and, well, 2x2 plus x3, oops, sorry, again, right, plus x3, I should have written x3 and equal to minus 1, say, right, and then say x1 minus x3 is equal to, right, say 3. Okay, right, now let's see whether or not this system is consistent. Okay, to make sure that we really comprehend how we can determine whether or not a system is consistent. All right, let's try to solve this. And what am I gonna do is, again, let's start to solve this system, and first write our system in the matrix form again and apply Gaussian elimination technique. So we have 1, we have minus 1 here, and we have 1 here, right? I denote the vertical line again, right, dashed or dotted, just to indicate that we have the right hand side values to the right of this dashed or dotted line. Okay, and so also, oh sorry, yeah, wait a minute, I made a mistake right over here. So what's the mistake here? So I forgot one value, right? So just be careful about that. Minus 1, and we have also x3, right? So here's the coefficient of x3, right? All right, now let's continue. Okay, now we have 0 for the coefficient of x1, we have 2 for the coefficient of x2, and we have 1, and we have minus 1. And for the last equation, we have 1, 0, minus 1, and 3. All right. Now, well, I will apply Gaussian elimination, and again, as usual, I'll look at the first pivot element, which is the first non-zero element in the first row, and I need to eliminate the values below it. But we already have 1, 0 here, so there's nothing to do for the second row for the time being. But I need to replace row 3. So let's perform an elementary row operation on the third row. Okay, so third row plus minus 1 times first row. Okay, this would work out, right? So what we get here, we get 1, minus 1, 0, 1. There, in other words, first row remains unchanged, and the second row again remains unchanged. We have not performed any operation there. 1 minus 1, right? And how about the third row? Right, what it is that this is 0, right? So this is 1, this is minus 1, and this is 2. Okay, so below the first pivot element we have what we want to have, and let's continue with the second pivot element. So we are done with the first row and the first pivot element. Now the second pivot element is 2 here, right? So the first non-zero element in the second row is 2. So this is the second pivot element, and I need to eliminate the values below it. So this one should be 0, right? And how can I do that? All right, let's continue. I need to replace the third row. So third row, right, should be third row plus, if I multiply the second row by minus 1/2 and then add it to row 3, then I will find what I want. So okay, minus 1 over 2 times row 2 will yield me the desired output for me. Okay, let's just make these changes, and again we have 1, minus 1, 0, and 1, and the second row again keeps its values, so no change here. And here we got 0, we got 0 again, minus 1 over 2 plus minus 1, it's minus 3 over 2, and we got 5 over 2 here. Alright, so what I have found. So let's check to see whether or not, first of all, we obtained the row echelon form, and the answer is what? The answer is yes. We have now the strictly increasing number of zeros from top row to the bottom row. So we are done with the elimination process, and what we have found. Let's examine the rows starting at the bottom, right? So at the bottom we have, you see, minus 3 over 2 x3 is equal to 5 over 2. So which means that, canceling this out, we have the value of x3, right? So x3 is equal to minus 5 over 3. And by applying back substitution method again on the above row, you see when I plug the value of x3, I will find the value of x2. And if I continue to do the same thing on the first row, again I will find the values of x1 and x2. And in this case, what we have? So in this case, we have the unique solution case, right? So when I apply back substitution method, I can find the values of each unknown variable one by one. And why is that? Because in each row there is only one unknown variable. So this means that we have the unique solution case. By just examining the rows we have in the end of the elimination process, we can simply determine whether or not this system is consistent. And how can we do that? In this case, as you noticed, we have the unique solution case, guys. So how would I understand that? Because when I look at the rows, I see that in each row, if I change the coefficients by applying back substitution method, I only have one unknown variable, which means that only one value for each unknown variable that satisfies both equations at the same time, which means that only one single solution we have, where we have the unique solution case, and therefore the system is consistent. Right. The system is consistent. Alright, now in the first example, okay, let's recap, guys. In the very first example, in the first system, we see that we have no solution. Why? Because we come to a point saying that the left hand side value is 0, but the right hand side value is something not equal to 0. So saying that 5 is equal to 0, which is always false. That means there is no tuple satisfying this system of equations at the same time. So we have the empty solution case, and therefore our system would have been inconsistent. In the second example, we see that we have the unique solution case. How would I understand that? Because when I am done with the elimination process and I look at the rows of the echelon form and see that there is only one unknown variable, if I apply the back substitution method in each row, so that means only one value of the unknown variable satisfies the equation for each unknown variable. Of course, I'm talking about each unknown variable. So that means that we have the unique solution case, right? So only one single point, and therefore the system is consistent. All right, and let's give another example, a third example. All right, let's say now our equation is say x1 plus x2 minus 3x3 is equal to say 4. And another equation, let's give another equation, guys. Let's say 2x1 plus 2x2 minus 6x3 is equal to say 8. All right, now let's try to decide whether or not the system is consistent. Okay, all right, is it consistent or not? All right, let's solve it. So then again, we apply the same strategy. Okay, applying Gaussian elimination method. First of all, we write our system in the augmented matrix form: 1 1 minus 3 4, and here we got 2 2 minus 6 and 8. All right, then, so, and in this case we don't have a row echelon form right now, right? Because the first pivot element is 1 in the first row, which is non-zero, which is a non-zero row, by the way. All right, and the below the first pivot element we have 2, so it should be eliminated. How can I do that? I need to replace row 2 by something else. So row 2 is replaced by row 2 plus, if I multiply the first row by minus 2, right, and then sum them up. Okay, what we have? So the first row remains unchanged, I just put the values here, but the second row becomes what? So this is 0, and this is 0, this is 0, and this is 0, guys. So let's examine this situation. What we have now? Well, I'm done with the first pivot element, and actually I reached to the desired result. Now my matrix is in the row echelon form, and I am done with the Gaussian elimination process. The Gaussian elimination process is over right here. But let's examine what we have in the last row. So in the last row, we have something like, on the left hand side, summation of zeros, right? We sum 3 zeros and it is still a 0, right? And on the right hand side we have 0 as well. That means 0 is equal to 0. But regardless of the selection of the values of unknown variables, this equality always holds. Then what this result signals to us is we have the infinite solution case here, because no matter what values we choose for the unknown variables, this would absolutely be satisfied, right? So what we have here, we have the infinite solution case here, right? So we have the infinite solution case. That's how we determine what kind of a solution we have. So we again examine the row echelon or reduced row echelon form. In other words, the matrix we obtained in the end of the elimination process. And look at the rows carefully to see what we have. And depending on the rows that we run into, we decide what kind of a solution set we have. Do we have a unique solution case? Do we have an infinite number solution case? Or do we have a solution at all? Maybe the empty set, right? The solution set could be also an empty set. So in this case, infinite solution, right? How do I understand? Because 0 is equal to 0 is always satisfied, regardless of the values of unknown variables. And how would we solve such a system, guys? Well, as you all remember from the previous 2 lectures, then we look at the rank and we look at the basic columns and the free columns, right? So in other words, basic columns and non-basic columns, and depending on that, we find the basic variables and the free variables, right? So in this case, as you notice, how many non-zero rows we have? We have only one non-zero row. And then what is the rank? And the rank is the value, which is n minus r. And n is the number of unknown variables. In our case, we have 3 unknown variables. And we have one non-zero row. So our rank is equal to 1, right? The number of non-zero rows in the echelon form or the reduced echelon form is equal to the rank, or the number of basic columns, right? Or the number of pivotal positions. It's the same, right? We have only one pivot position here. And so what I got? So what I got is, guys, so here is the number of, and this subtraction, in other words, n minus r, is equal to what? We decide what is the number of free variables here, right? So we have 2 free variables. And how many basic variables we have? So we have 3 unknown variables. And if 2 of them are free variables, then we have what? We have 1 basic variable, right? We have 1 basic variable. All right. And what are these variables? So how would we decide? As you remember, the basic variable is the variable that corresponds to the basic column, and in our case we have 1 basic column, right? Because we have only 1 pivotal positions, and our basic variable is x1, whereas our free variables, 2 free variables, are x2 and x3, right? We all remember that, all right? So then what are we gonna do? After deciding what these variables are, then we try to somehow express the basic variable in terms of free variables by applying back substitution method in the row echelon or the reduced row echelon form. And the last row has only zeros, so I just move to the row right above it, the first row. So let's write it. Okay, so in the first row, what I have x1 plus x2 minus 3x3 is equal to 4, right? So if I want to express basic variable x1, then all I need to do is just move this free variables along with their coefficients to the right hand side of the equality, and then x1 is equal to 4 minus x2 plus 3x3, right? And this is what I get. So actually this is what I found, right? This is my basic variable. In other words, I expressed our basic variable in terms of free variables. So then, to find the solution again, what should I do? Here's my solution set, as you all remember, and this is, as you remember, this is x1, x2, and x3, right? So I just put the values that I've just found here. So instead of x1, I put the value, right? 4 minus x2 plus 3x3. So, and then we got x2 here, and we got what? We got x3 right over here, guys. All right. So here's what I got. And if I want to express this as an algebraic sum, what I need to do is just decompose this, right? So I can decompose it something like 0, 0, and for the x2 minus 1, 1 and 0, and we can also have 3, 0, 1, and this is x3. So changing these values, if we change x2 and x3, so in other words x2 and x3 can take on any real values, and then summing this up, any combination in this form would yield us a result, a solution, right? So we have an infinite number of solutions in this case. In other words, suppose, for instance, I take x2 is equal to 0 and x3 is equal to 0, then what I got is, in this case, I have this 4, 0, 0, right? This is just one solution. And if I plug it back here, as you notice, if I put the value x1 is equal to 4, then x2 and x3 is equal to 0, then it is satisfied. And the same thing for the equation below it, right? For the second equation. And this is just one solution. I can change the values of x2 and x3, and I can have infinite number of the solutions. So say if I take x2 is 1 and x3 is 1, then what I get? Then in this case, this time I get 0 if I take x2 is equal to 1 and x3 is equal to 1, right? Well, by the way, this is not 0, right? So 4 times 3, 7 minus 1 is equal to 6 here. So, right. Yeah. So this is the thing, right? 6, 1, 1, right? 4 plus 3, 7 minus 1, 6. Okay, that means if you plug 6, 1, 1, and again it is satisfied as we see, right? 6 plus 1, 7 minus 3 is equal to 4, and again 6 times 2 is 12, plus 2, 14, and minus 6 equal to 8. And if we can continue in this way. So in either case, we have an infinite number of solutions. And again, the important point here for me is that how we can determine it. Because we already have learned about how we can solve the systems regardless of what kind of a solution set we have. We can have the unique solution case, we can have no solution, we can have infinite number of solutions. But the way we decide what kind of a system we have is now much more clear to each of us. Okay, so in the infinite solution case, we look for some row saying that 0 is equal to 0, right? Something like that in any row. And for the unique case, you know, after we are done with the elimination process, in either case, by the way, we look at the rows. If we have one unknown variable in each row of the echelon form, then we have the unique case. That's absolute. And for the empty solution set, in other words, no solution, we look for some rows saying that 0 is equal to something else which is not equal to 0, right, on the right hand side. So something like 0 is equal to 5, 0 is equal to 7, that doesn't matter. So which means no tuple satisfies this equality because it is already false. And based upon the result, we say that a system is consistent or not. And the thing is, if a system has at least one solution, which means that if we have the unique solution case or the infinite solution case, then we say that the system is consistent. While we say that system is inconsistent if we have no solution. Alright guys, see you in the next lecture, and until then, have fun.